Okay, welcome back. Today we will be talking about cognitive models. So after the first half of the seminar, we talked about many stuff about statistical models, one parameter and multiple parameters in the example of binomial distribution and normal distribution regression. And we talked about the last time. So today we will be talking about cognitive models, and we will continue through the end of the seminar, okay? Good. So the warm-up part, it will take long if I take the time. So I guess if you have time, all the stuff I mentioned, the binomial model and the regression and the other stuff, please do take some time to revisit the materials. And if you have questions, then feel free to come back to me, and I'd be happy to answer the questions. So let's start with the cognitive models part. And this is something that you've been expecting or anticipating from the beginning, I would believe. So the idea of cognitive models, or in other words, sometimes people call it computational modeling. So this might be the term that you hear about relatively often when you read papers, when you go to conference, when you apply for a summer school, for example. So everything is about computational modeling. And you might be wondering, but well, why nowadays everyone is talking about computational modeling? So for one reason, it might because it sounds a little bit new, a little bit fancy, and a little bit complex, right? And it is a little bit, you feel like it is a little bit more advanced relative to traditional methods. So those are the feelings, and those are some kind of the bias if you have not heard about computational modeling yet. So those are some common ideas that is around here and there. But I would like to argue that, so the idea of computational modeling is really never new. So for example, when we were talking about physics, right, or whatever we learned from school, from high school, and we know that we were scientists from a few hundred years ago. So they were trying to describe and also to predict the trajectory of some planets, right? So how the planets are moving around the sun, and if that is true. So one possibility is there's a circular orbit, so there is a round, and another way is, for example, something like this, right? Elliptical. So both of them, they are honestly models. Each of them, they have a formula. Each of them, there is an equation, and you could write down the equation of a circle. You could write down the equation of elliptic. So the idea is to use here. So the idea is that those scientists from a few hundred years ago, and also the scientists nowadays, so both of these groups of people, so scientists in general, so we are trying to use mathematical models to approximate certain processes. It can be physical, something illustrated here, or it can also be something mental in terms of cognitive process. And then the goal is always to explain and also to predict, right? So if the goal is to try to approximate the trajectory of the planet, if we know that there is one model that could approximate the movements, and then we could even predict what the next location will be according to this model, assuming the model is accurate. So those are powerful tools for us to better understand some processes, and physical or mental, as I said. Okay, so those models, like here, they are many hundreds of years ago, and they are indeed computational models. And so it has been around for many, many years. This is my take. And why we thought a little bit that computational models might be something new for us, it is because it is new for the field. So the idea of computational modeling is kind of old, but the idea of computational modeling in psychology or in cognitive neuroscience, this is a little bit relatively new, okay? And if you heard about other terms from other whatever places, there's a field called systems neuroscience. And systems neuroscience, they are actually the hardcore computational neuroscientists because they use mathematical models to approximate how the neuron works, not really behavior. So you see the different levels. So here on the graph, I show you the approximation to a physical process. And what we will be talking about through the end of the seminar is the process of behavior. So what produces behavior, choices, reaction time, for example. And at the other level that I mentioned is to approximate how the neuron works. So how the neuron fires and how the neurons communicate with another cluster of neurons, for example. So those are different categories. The difference is only that the object, so what we are trying to model, what we are trying to approximate, this is different. It can be physical, can be mental, can be neuronal, but the model, they are just some equations, right? According to what you want to model. It can be like a circle in this case, it can be a binomial model that we will see at a later instance. It can be something else when you are trying to model neuron activities, firing rates, for example. Okay, good. And if we understand this part, so let's talk a little bit more about cognitive modeling. So as I said, cognitive model, you can interpret that as the computational modeling of behavior. So why we are trying to model behavior? Because behavior is the window to look at cognitive processes. So this is the link. So this is how we call it, okay? And what is cognitive modeling? So after the brief introduction from 2 seconds ago, I guess you already have more or less one rough idea about what cognitive modeling might mean. So let me just introduce here, briefly talk about that. So assume that there is a participant who is visiting the laboratory, who is making some button presses, who is making some cognitive tasks. Reward learning, for example, the one we've seen. So the participant is observing 2 choices and he or she is trying to figure out which choice stimulus will be more rewarding. Okay, so this is the task, and then the participant is making the button presses, good. And we could observe some behavior from the participants. We could observe which buttons or which stimulus the person is choosing. We could also measure some brain activities by using some neuroimaging techniques. In this case, I show you the fMRI, the functional magnetic resonance imaging. So we could record the both signals to reflect the neuronal activity, okay? And we all know that either the behavior we observe or the brain activity we observe, they come from the brain, right? Otherwise, what do we observe? So there are something that is happening in the brain that produces the behavior and also the brain activity, honestly, obviously, good. And in some kind of traditional way to analyze the data, let's say traditional psychology or traditional cognitive neuroscience, we use the behavior, right? So we use, don't worry about this. So we use the behavior to infer what might be happening in the brain, okay? So let's say in another example, like we ask the participants to watch different pictures. So one category of pictures might be just faces, human faces, and another category of pictures is houses, something like the house, objects. And we take the both signal measured by the MRI machine, and we compare the brain activity related to face versus the brain activity related to the house. And we just make the contrast to see, well, where the difference is, okay? So this is to use the brain activity or the behavior. We could also use the behavior to infer what might be happening in the brain. Okay, this is the way to analyze the data traditionally. Good. And sometimes the behavior that we observe, or sometimes the mental or the cognitive process that is underlying the behavior, it is rather complex, and it is not as simple as we observe. So in the button press example, we only observe choosing left or right, 1, 2, 1, 2. So A or B, something like that. There is a kind of pattern because we could use the A-B choices to infer learning. If the participant was a little bit more random, exploring what is correct, what is incorrect, but at the later period of the experiment, the performance might be increased because the participant is learning a lot from the task, right? So there might be a pattern. We could infer what might be happening, but why at a certain choice, participant is choosing A, not B, or at a later stage, why the participant is choosing B, not A, if this is a reversal task, okay? So why is that? Why we only observe A or B, but maybe we could assume something more complex in the brain. Okay, good. So then that's the place where it comes to cognitive models. So the idea is, okay, we propose a formulation. Okay, rather than calling it a model, we could say just some formulation. So the formulation is with the goal to approximate what might be happening in the brain when the participants, when individuals are doing some tasks. Okay, so here let's assume this formulation is related to the two option choice reward learning task. And what we could do is the same idea as we did for the regression model. So we could let the model to generate behavior. So the model is a formulation tool. You can imagine, as for now, that as a black box. So there is a formulation, some formulation to the black box. So you, as a participant, you see on the screen, there are two options, left or right, left or right. You can make a choice. So this black box or this formulation is like another you that is trying to approximate you. So the black box, the formulation also sees two choice options on the screen, and the formulation is now trying to make choices. Okay, so we could basically, this process is called to let the formulation, let the model generate choices, choice data or behavior data. Okay, good. So when we ask the formulation to generate choices, and we could then compare if the generated choice is similar or dissimilar compared to your actual choice. Suppose you are the participant, you see two choices, you make button presses, and there is another guy, not a person, but the guy is a formulation. The formulation sees the two choice options, making button presses, A, B, A, B, and then we could compare the two sequences of the choices. One set of choices is coming from you, and another set of choices is coming from the formulation, the model. And if these two set of choice sequences is similar, or okay, this error doesn't matter. So if the two sequences of choices are similar, we could then say, well, this formulation is doing a relatively good job in approximating what might be happening in the brain. Okay, so this is the rough idea. Not really rough, I guess. It's quite okay idea of cognitive modeling. So let me just briefly summarize. The goal is to trying to understand what is here, right? What is happening here. So why the participants are making choices in that particular way, not in a random fashion, for example. So we are trying to understand this. So this is our goal. And we cannot really open up the brain to look at the brain, right? Most of the time. So we look at the behavior. And looking at behavior most of the time is not really satisfying because behavior is a little bit simplified. And then we are trying to come up with a formulation, namely a model or a cognitive model, so with the goal to approximate the brain. So if the model's behavior here is resembling the actual behavior we observe from human participants, then we could conclude, or we could argue, that this formulation is doing a decent, relatively decent job to approximate the cognitive process. Okay, good. So our goal is here, and we are trying. Our goal is here. We observe here, and we are trying to come up with something here to approximate the brain. Okay, good. And now, if you ask what is the goal of cognitive modeling, well, the ultimate goal is always to use some formulation to understand the brain, but in practice, the goal is to come up with reasonable models. So here, I guess this will be our focus. So how to come up with some reasonable model that could approximate the brain. Okay. So one goal is how to come up with a reasonable model. The other goal here is our learning goal, I mean. So the other goal is to implement it in the programming language that we've been focusing. So that's Stan, to use MCMC and to write down cognitive models, and then we run it and we fit the model to the data, and use the model as a generative tool also to look at the brain. Okay, so in particular, if we have some other measurements, so let's say here, I didn't really talk about too much about the fMRI. So the cognitive modeling part doesn't really deal with brain imaging data. So the cognitive models, they only deal with behavioral data, button press, for example, reaction time, and we could derive some internal model variables at a later point and then correlate that with functional neuroimaging or EEG, MEG, if you are interested in. So everything, nearly everything is possible, if not everything, if not really everything. But as far as I see, so this kind of analysis using model-derived variables to correlate with other modalities of measurement. So this kind of method, it is called model-based analysis in our field. There are model-based fMRI, model-based EEG, model-based MEG, model-based eye tracking, model-based also mouse tracking. So you name it. As long as there are some external modalities of measurement rather than behavior, besides behavior, you could use model-based analysis to just link some, to draw some connections. Okay, good. Are there any questions? So what is the benefit over building models from observed behavior, as on the left? So the left is the observed behavior, yes, of course. And so the benefit of building the model is trying to understand why the participant is making the behavior. So for example, if we have 10 trials, only 10 trials in the two option choice task, and the participant is making choice A and get a reward, and choice A again and getting a punishment, and then choice B and getting a reward, and choice B getting punishment, another punishment, and switch back to choice A and reward. So this kind of task data, right? And those are the task data. And we might be wondering why the participant is making the choice like this. So you could say, well, there is a strategy. So you can judge from the paper you read. There is the strategy called win, stay, lose, shift. Win, stay means if I win by choosing some option, I stick with it. I could repeat. And lose, shift means if I lose, I go to the alternative. This is a strategy. This is, in fact, a reasonable strategy because you would like to repeat your previous success and you would like to avoid punishment by stepping away from the previous failure, right? This is a reasonable strategy. But there is not really a way to go into the subjective value of what participants are thinking about. So this is a little bit more abstract, I guess. So the idea is in this way. So if you heard about utility or subjective value, it might be easier to understand. But in general, in short, the idea of utility or subjective value is that if I give you two options, and you will mentally imagine or calculate which one will be more likely to give you a reward. So in other words, which one is more valuable, right? In your opinion. So this is called subjective value or utility in economics. There are some slight differences, but it's not the focus here. You can just imagine now they are the same thing. So if at some period of the experiments, after choosing 3 times of A, and you observe 2 rewards and 1 punishment, so you might be having a subjective value of the choice option A. And then you compare this subjective value of option A relative to the subjective value of option B. And then you make the choices according to the subjective value. So the goal to build the model is to calculate what are the internal steps, like calculating, for example, calculating the subjective value or calculating something like a prediction error. We will see that later, so it doesn't matter. So if we look at only the behavior, so most of the time we look at a summary statistics in the sense that if we observe or measure 100 trials per participant, and we calculate how frequent the person is choosing the best option. And we could take a summary, we could take a proportion. This is in fact what we did on lecture 2 or 3 in the R exercise. We calculate one number, the average accuracy per person, okay? So using the 100 data points, because we have 100 files, we get only one number. So this is a huge reduction of the data, and we lose all those resolutions of the trial-wise data. Okay, so those are in the literature called trial by trial analysis, if that's possible. If we use summary statistics, most of the time it is not really possible to do trial by trial analysis. To do this trial by trial analysis, because we know that there are information that is contained by the trials, okay? What we want to do is to, okay, here we build a model, and the model is trying to approximate the behavior trial by trial. So the model is predicting on trial 1 why the participant is choosing A relative to B, and on another trial, the model is predicting choosing B relative to A, for example, as my example. The model is making predictions for every single trial. And in this way, we have the trial by trial data and the trial by trial internal information to see the behavior. Okay, any other questions? There's a comment. Similar to this network, okay, that we have the results of the gathered behavior data, and it is compared to the results the model generates, which are then used to improve, update the model. Okay, this is a good question. I'm not really sure, because first of all, I'm not really familiar with the machine learning field. Second of all, I don't think the comparison might be, wait. Yeah, in a way similar, yes. Yes, I think so. Yeah, I think so. Yeah. But the procedure is a little bit more complex, I think. Actually, is a little bit more complex than what you wrote. So okay, the idea is we have the behavioral data and we want to model it, okay? This is the idea, it's obvious for now. We model it by using one model. But most of the time, one model is not enough, or maybe the model is not really doing something okay, and the model is poor. And we would like to improve the model. And how we could improve the model, we could first, so there are two approaches. One approach is to look into the literature. So what are the models that are relevant to your task, to this task? So maybe that proposed model is performing better than the one you have currently. So this is one approach, going back to the literature. Another approach might be the way to go a little bit bottom up, to do a little bit more data driven. So we have the actual behavior, we have the model produced behavior. We compare the actual behavior as opposed to the model produced behavior. And if they match, that's good, everyone's happy. If they do not match, and then we could go back to the model to see why or how there is a mismatch between the observed data here and the generated data. And then use the trial by trial information to improve, to make it better. And this improved model is in fact a second model already, because it is different from the one we did initially. So this is already a second model. And we compare which one is good, which one is not good. I guess in this sense, it sounds similar. Yes. Yeah. Other questions? Yeah.
I think it's easier to maybe say it out. I mean, maybe I'm just too stuck in this whole frequentist thinking, but when I imagine a model, is this a series of regressions or comparisons?
I don't understand the question.
Yeah, I'm still not completely sure what this, like, how a model looks, I think.
Yeah, okay. In this case, so in the example we will be talking about from like 5 minutes later, you will see how that looks like. So
okay, sorry.
Now it is not really a regression, but it can be taken the form as a logistic regression in the final step. But there are some steps before to calculate the value. So the value part cannot be addressed by any kind of regression, but how to link the data to the model, it takes the form of typical statistic models. So the choice data AB is just like binomial, right? The coin flipping, head tail, that's the same. So in the previous example, the head tail, the coin flipping example, that follows the binomial. There is a theta parameter, the proportion, right? The proportion. And in that particular case, the proportion is a free parameter that we are trying to estimate. So here in this cognitive modeling part, there is also a theta, but the theta itself is not a free parameter. So the theta is calculated by some other steps, some value calculation, some prediction error calculation. So you will see that later. Does that make sense? Yeah, okay, cool. Other questions? Okay, good. So if not, let's go forward. Okay, so as you could see, maybe you are familiar with this kind of saying. So this is George, and he is a British mathematician. He once mentioned something like, okay, essentially all the models are wrong, but some of them are useful. So the idea is, it is never possible to really come up with a model that's completely, exactly approximate how the brain works. Otherwise, the biggest problem of the world, of the century, is solved. And it's not really possible so far, and might be for the future. I have the hope. But all the models are simplified. Okay, all the models are simplified version of how the brain works, and the models are specialized in the sense that if one model is perfect for producing or predicting the button press behavior in the simple rewards learning task, if there is a best model for that, this model is very unlikely to also predict behavior as a memory task. So because it's not specialized as that, okay? So in some other instances, we know the AlphaGo and the machine or the artificial intelligence, AlphaGo, and that is really good at playing the Go game. But if we ask AlphaGo to do something else, to do another memory task, okay, maybe the performance is not really ideal. So all those models are, first of all, simplified, second of all, specialized, okay? And also might not be true. So those are something that you have to keep in mind. So this is what we know about. So all the models are wrong, but some of them are useful. And if you do not like the word wrong, you can say, well, essentially all the models are imperfect, but some of them are useful. So the models, they are tools. They are tools to understand how the brain works. But we use one tool to understand how the brain makes decisions, A or B, and we use another tool to understand how people memorize word, memorize items, memorize something else. So those are tools. They are imperfect, of course, but they are really useful tools. If we do not have the tools, the way to understanding the behavior is a little bit reduced, honestly. So even though they are imperfect, they are in fact useful, okay? And then from this moment on, we will be talking about one of the imperfect but really useful, sometimes really people see it as the most influential and dominant model in the field of neuroscience, cognitive neuroscience, psychology, also even artificial intelligence. And that is the reinforcement learning framework. Okay, so we will talk about that. We will talk about the reinforcement learning framework for, I guess, 5 or 6 lectures, if we still have that many. Yeah, but till the end of the semester. Okay, good. We will mention a little bit some other frameworks, some other categories of models, but most of the time we will be using the reinforcement learning framework in our class. Good. So there's a very short story, maybe just 2 minutes. So the term of the reinforcement learning model is popularized by the book written by Sutton and Bartle more than 20 years ago already. So 1998, and 2 years ago they finally finished the second edition of the book. So if you would like to read, if you're interested in, so go for the second edition. So what is interesting is actually those people, they are computer scientists. So they wrote the book about reinforcement learning really in a computer scientific way, CS way. But very interestingly, what interests is that so they didn't really anticipate how influential this computer scientists oriented book reinforcement learning is so influential to the field of psychology and cognitive neuroscience. They didn't anticipate that, but they see there is a huge growth in our field of using reinforcement learning models. So then if you look at the table of content, you will see from the second edition, there are 2 chapters, 1 or 2, I forgot, but there is a huge section about how to use that in the field of cognitive neuroscience and also artificial intelligence. So that is very interesting. Good. This is the end of the very short story. But remember here, the year of 1998, we will see that for some other reason later. So that is the place to see that, okay. Here I show you a graph. So there is a short kind of review paper, and he and his colleagues, Stefano and his colleagues, so they summarized publications in the past relative to, here is 2000, maybe 15, I don't know, doesn't matter. So here, they summarize the publications that are focusing on, in this color, cognitive, and in this color, blue, cognitive together with computational models. So we see that relatively, the papers who are focusing only on the cognition part, the cognitive part, it is a lot because it has a long history, okay? It has a long history. But you see the growth of using cognition and together with computational models, even though it is relatively lower at most of the time in the history, but the growth is really faster. So the growth is steeper. Every year we see more paper using cognition together with computation than paper who is using or focusing only on cognition. And at some point, I guess there will be the cross. You see more the color of blue relative to the less color of purple. And then this is the growth. So this is kind of the speed of the increase. So one interesting observation is if you look at the x-axis, which is the year of publication, and if you also recall the year of 1998, which is the year where the book came out, the book of reinforcement learning. So you see here, so maybe, so I have to say that this is only my interpretation. I have never seen anybody is trying to link the reference of the year to make this kind of argument. This is only my interpretation. So take it, don't really take it very seriously. So as long as at least from my interpretation, I see here after the year of 1998, so most of people, they are trying really to understand what the book is about, right? Because this is really a book from another field. So you see here, not really too many people are just like using models like something complicated from computer science. But maybe after a few years, people are trying to digest what the book is about from two computer scientists. And then we see here there is a huge increase because really that's from the year 2005. I believe that's the first paper who is really trying to use the concept of reinforcement learning model to understand human behavior. Okay, around here, 2004, 2005. And then after that, there is a huge increase. Okay. So yeah, this is my personal opinion. And this is another example to say, well, it's not always true, but maybe it's possibly something happened in the past is the cause of something that's happening in the future. I don't know, personal take. But believe it or not, we know that by fact that the increase of using cognition and computation is faster than using cognition alone. Okay, good. And so today is the end kind of May 2020, and I show you a few examples of using computational models in publication this year, very recent. So we see here, this is from 2 months ago, it's March 2020, and another one, this is also March this year. This one, March again, well, I guess I chose those examples on purpose. This is also March. So basically 2 months from today on, we count backwards. 2 months ago, I just randomly, not really randomly, but kind of chose on purpose the papers who are really using computational models. So if you really look at the papers, we see that the 3 out of the 4 publications, so they use reinforcement learning models. It seems like after 20 years, this is still kind of very useful to understand behavior, okay? And by the way, if you're interested in those papers, a really great paper to see some current or recent usage application of reinforcement learning models. Good, especially this one. This one I think I really recommend. But this one, the one here, bottom left corner, this one is not an empirical paper, so it doesn't really talk about experiments per se. It is instead a review article. So, you know, review article to review publications, to review studies from before. And this review is in particular focusing on social learning and across species, human, monkey, and animals and mice, for example. And so the authors, so here, these 2 authors, they're really trying to use the reinforcement learning framework together to connect the social learning field in both human and non-human primates, or also other rodents, for instance. It's really good reading if you have the time. Good. So now let's go to the details. So if you look at the literature, you look at the book, if you read some other tutorial of reinforcement learning, most of the time you will see this bandit example or bandit task. So in this case, we have a 2-armed bandit task. Those are bandit machines or slot machines. If you like those, you see those in the casino, for example. So the assumption is that these 2 bandit machines, they're not identical. They are not identical in the sense that one might be giving you reward more often, and the other one might be giving you reward less often. And this can be translated into the 2-choice, the 2-option forced choice task. So they are the same. So it's like one option is a better option, the other one is a worse option. So there are some probabilities, you never know, but you could learn from using the feedback. Okay, so this is the link. We talk about that later. But for now, there are 2 machines. There are bandit machines. There are 2 slot machines. If you are standing in front of the 2 bandit machines, you have no idea yet which one is a better machine, which one is a worse machine. What do you do? So what you do might be that, okay, you play with the bandit machine. You pull the lever and to see whether you get a reward or a punishment. Suppose that you don't really have to pay for money you pay some money to play. You just play, okay? That's the assumption. You play with bandit machine A, you get some feedback, and you use that feedback to reinforce yourself, to educate yourself, or to teach yourself, in the sense that is the machine good or is the machine bad? So if you play it, if you receive a positive feedback, meaning you get money, you might be wondering, is this machine a good machine? But maybe at the moment, it is a good machine because at the very beginning, when you were trying to decide which one you want to play, left or right, you might be deciding at random in the first place. Because if you are standing in front of the 2 machines, they look identical. You have no idea which one is better, which one is worse. You just play at random. Okay, so if you choose the left one, if you get a positive feedback, this left machine is making a better outcome than your prediction. So it is better than your prediction. And then this one, you use the difference between what you actually got and your prediction. You use this difference to educate yourself, and then you make the next choice. I will explain later what I mean to use the difference to educate yourself. But for now, let's just revisit the example again. So you have the 2 machine, you play with it, and you use the feedback to educate yourself, and then to make further choices. So this is the general idea. Good. So this is something like a simple task often used in the laboratory. So you make repeated choices between the n options. In this case, n is 2. You make a repeated choice between the 2 options, A and B, and next trial A and B, and then 1 trial later A and B. You make repeated choices, maybe 100 trials, and then you get money. This is a goal. Your goal is to get as much money as you could. So this is a task. This is also the instruction that you would tell the participants. Okay, so those bandit machines, they have properties. One property is the reward amount. So if you win, you could win, for example, 1 cent. If you win, but maybe you could also win 50 cents. Sometimes, if you're lucky, you could also win €2 in this case. What differs is the magnitude of the monetary unit, the amount of money you get. Another property is the probability. So in this kind of tasks in the literature, I guess also in the paper you read, you reviewed, there is something called reward probability. So reward probability simply means the probability to obtain a reward. If the reward probability is 70%, as one example, that means on average you will receive 70% of the you will receive money for 70% of the time, and the other 30% of the time you will receive nothing, or sometimes punishment, depends on how the task is constructed. Okay, and if you understand this, let's say, well, you have a machine that has a 100% reward probability. Oh, this is really a good machine because every time you play, you will for sure get a positive reward. And then in this case, this is ideal world, okay? And in some not ideal world, maybe there is a machine that has a 20% reward probability. That means only 20% of the time on average, if you play 100 times, on average 20 times, you will get a reward, and 80 times you will get nothing or punishment. Okay, so this is the reward probability. The reward probability is very important because we are then trying to infer by playing. We are trying to infer what the reward probability is if we do not really know the reward probability. So when I'm trying this, I guess I'm confusing you in one aspect. You have two roles for now. So sometimes when I'm describing this, I'm considering you are the experimenter. But another time, when I'm describing this, I assume you are a participant. So maybe I didn't really say that explicitly, but I guess you realize that I mean different things. So if I make it clear, if for now we are experimenters, if we are the people who is constructing the task, we for sure will have to know which one is the better option, which one is the worst option. So we predetermine the reward probability of the two options. We could determine one is 0.7, the other is 0.3, to sum up to 1, okay? We determine, and we give the task to the participants, and then they're playing it. Okay, now let's turn the role. If you are participants, you receive the task from some guy in the Faculty of Psychology, and you are sitting in front of the computer, you are seeing two choice options. You have no idea which one is better, which one is worse, right? And then what you do is to play with it and receive feedback, and use the feedback to learn, to try to infer which is a better option, which is a worse option. And if your learning is sufficient, if your learning is good in a way, then you will always, if you are like kind of rational, you will most of the time just stick with the one that you believe that has a higher reward probability, because if you stick with that one, on average, you will gain money. So this is the two roles of this kind of task. One as experimenter, the other one is as a participant. Okay, good. Now we can go back to the slides. So the simple task, most of the time the participants is try to win money, right? So this is in the literature also called goal-directed learning, because there's a goal. The goal is directing the behavior, and our behavior is trying to approach the goal. So it is called goal-directed behavior or goal-directed learning, because here indeed we have learning involved in this task. And so now let's put all of us in the shoe of a participant, okay? And imagine that we are participants and we are standing in front of the two machines. We are sitting in front of the computer seeing two options. We have to make a choice between the two options. And what can be our strategies? What can we do to figure out which is a better option, which is a worse option? Okay, what can be our strategies? So what we do is that if I see the two options, I basically make a prediction. I make a prediction to predict which one might be giving me reward, and which one might be giving me punishment on the other hand, okay? And if I'm seeing the two options for the first time, my prediction is, well, these two guys are the same. These two guys are indifferent. And then I make a random choice. But if at other time, if I am at some other stages of the task, I've already learned something from feedback. If I say, okay, the prediction at the current moment is that this one, the left one, maybe has a higher reward probability or utility or subjective value, and then this one has a lower subjective value. So then those are basically my predictions. And next step is to behave or to act in accordance with the prediction, okay? So one possibility is to choose the best. If I know one is higher, the other one is lower, I basically choose the higher one, okay? So this is one of the strategy. And after you make a choice according to the best, you will see the feedback. The feedback, if the feedback is a reward, this basically reinforces your belief that the left one is the better option. So this is learning, right? You learn from observing the belief. You learn from observing the feedback, and then you use this feedback to update your prediction. And if you choose the left one because the left one previous has a higher value, and then if you receive a negative feedback, and that basically means you should lower your prediction because that gives you a negative feedback. Okay, good. So the strategy, let me just repeat. You predict which one is higher, which one is lower, which one is better, which one is worse, and then you act in association with, in accordance with your prediction. And then you receive feedback, and then you use your feedback to educate yourself and update your prediction. And then you repeat. Okay, good. So to make it as a framework, because we are trying to understand everything in the reinforcement learning framework. So far, I only told you the task, the toy example, the bandit machine. So how to connect everything together in the framework. So conceptually, if you look at reinforcement learning literature, you will see some graph like this. Okay. So there are two parties, let's say two parties. So one is the agent or the participant or yourselves, for example. So before you just enter the experiment, you are just basically a person like innocent about the experimental task. Good. The environment in our current setup is the task environment. So there are two bandit machines, two slot machines. One is better, one is low. One is better, one is worse. So this is the environment. And what is your goal? Your goal is to get as much money as you could. So this is your goal. And what do? You interact with the environment by making some actions. So you choose the left relative to the right, and then the action will result in a feedback. And then the feedback is observed by you. So you either observe a reward or a punishment, and then you use this feedback information to make a further action, and then the action will result in another observation or feedback, and then goes to you, and you make another action. So this goes multiple times, so iteratively. Okay, good. And we could also tease apart this process into multiple steps, or decompose the decision-making process into multiple steps. We start from here, okay, here. The very first step, we can say we are now trying to represent the problem. Represent the problem means you figure out what you're supposed to do. So if you are sitting in front of the computer, if you see two choice options, you are supposed to make an action. You are supposed to make a choice between left or right, with the goal to maximize your outcome. So you are supposed to do this, right? You are supposed to make a decision in the decision-making task. Here, the second step, the valuation. The valuation is similar to the prediction, as I mentioned previously. So prediction is to predict which one is a better one, which one is a worse one. Valuation means the same thing. You value which one has a higher value, which one has a lower value. So you do some valuation. Valuation, in other words, means the computation of value, okay? You compute which one is more valuable, which one is less valuable. And here, this is you act upon your value. So you make an action, left or right, based on your valuation. Here, the last step is to observe the outcome. according to your action. If on the current trial, if you choose left, you get a reward, and if you choose right, you get a punishment. It can be like that, okay? Those are the feedback. And here is the important part. You use this feedback information to educate yourself, to update your prediction, to update your valuation. So this learning goes back to the next trial, and then you use the updated valuation. So here, because you've already seen something, you learn, and this valuation is not updated. It is the new one. It is the new value, and then you use the new value information to make new tries, and then you see new outcome, and then you go back and forth through the end of experiment. Okay, those are the tasks. Good. Right. As one example, so in the experiments, usually we do not really show them the bandit machine. We show something simpler like this. So this we have seen already. So we show participants, for instance, the abstract fractals, like this abstract just symbols, okay? Abstract symbols. They differ maybe in color, in the shape, but for most of the participants, those colors or shapes, they don't really mean too much. They are just like two random things. And if I have no information, which one is better, which one is worse, I'm supposed to choose to make my choice randomly at the very first trial. Somebody may have their color preference, that's fine, because this can be averaged, I think. Somebody, if they prefer blue, some other people, they prefer yellow, this can be averaged, this doesn't matter, okay? So we basically assume these are identical at the very beginning. And then participants make a choice. If they choose left, they get a reward. And they go to the second trial, see these two options again, and then make a choice, and they receive a punishment in this case. So this is the typical experimental procedure or setup we see from laboratory when we only have two choice options, as simple as that. Okay, good. So let me just summarize what we have talked about, because I've been talking for, I don't know, 20, 30 minutes. So we started from introducing cognitive modeling, and we mentioned that cognitive modeling is the computational modeling of behavior. We also mentioned that computational modeling is really never new. It has been around for a few hundred years, maybe in another field, not in our field, but it's not really new. And it is always what scientists are trying to do, to use some formulation to understand the process, okay? So in our case, we are trying to use formulations to understand the cognitive process and then the behavior. Good. And we mentioned that out of a bunch of computational models of cognition, there is one specific category of models that is called the reinforcement learning model. It is in fact a framework. And in the reinforcement learning model, in essence, it describes the relationship between an individual and the environment. So I can go back, this one is important. So here, the reinforcement learning framework describes the relationship between an individual, a person, and the environment, the experiment, for example. And it describes that the person is trying to use some feedback to educate him or herself, and then to make further actions. And the goal is to always maximize the outcome. And we used one example to illustrate the idea of the reinforcement learning task. So the example we used is the two-armed bandit task, or two-armed slot machine task. So there are two slot machines, or two abstracts symbols. So you are supposed to make a choice between the two symbols. And you use the feedback information to educate yourself and make further predictions or further choices, okay? So this is really the simplest example in the reinforcement learning literature. And the reinforcement learning is in fact a family of models. There are actually a lot of complicated reinforcement learning models. And we do not really talk about that, but we just focus on the simple ones. And if you're interested in, so feel free to ask me, and I can send you other papers to go a little bit more in depth. Okay, good. Are there any questions by far? Yeah, there's a question I didn't see. So do the Bayesian models usually show more coherent results than frequentist results in psychology? I guess this is not a random, sorry. This is a general question, right? Not related to the model here. Just in general, you would like to know the difference between the Bayesian and non-Bayesian methods. Is that right? If you could elaborate, you can speak. Yeah, go ahead.
Yeah. Yeah, I was wondering if there's like, for example, for the core experiment for reinforcement learning, if there's like one model which has one code you would put in Stan and which is agreed on by everybody, and then you do this variation, which is seen as the variation, and everybody would do it the same?
Yeah, so we feed the model to the data and we get the parameters per person, and we might get different parameters per participants. So at the later point, we will see that there are parameters. I can tell you now, so there's a parameter called the learning rate. So maybe one person, according to the data, the fitted learning rate is 0.3, but maybe for another person, the fitted learning rate is 0.4, and for a third person, the fitted learning rate is 0.25, for example. So the algorithm is the same, but the way the algorithm is implemented, there are individual differences in terms of the value of the parameter. So let me just put another example. So I guess that's a little bit more easier, much easier to understand. So we know linear regression. Okay, so linear regression is y equals a plus x times b. Okay, so this is the equation. Good. And let's assume that we have multiple data points, and we have data from what's the example I could tell? Okay, let's just use the weight and height example, and we can have the weight and height from different regions in the world. We can have the weight and height regression in Austria, in Germany, in France, and in China, Japan, US. Okay. So let's assume all those weight and height regression, they always follow the regression line. They always follow the same y equals a plus bx. The regression formula is the same, but the value of the a and b, so the slope might be different according to the country, right? Because different locations, they might have their own geographic property and nutrition, blah, blah, okay, whatever. So this property of slope and intercept, they might differ. So this is the similar idea here. So if we use the same reinforcement learning model to fit the model to the data, the way how the value is updated, how the prediction error is calculated, it is the same. It's like y equals ax plus b, a plus bx. It's like that. But how this is implemented? So what is the slope? So the slope of person A or country A is different than the slope of country B. So the learning rate here is the same. So the learning rate of participant A could be different relative to the learning rates of participants B. Does that answer the question?
Yeah, I was more wondering if, like, in this computational modeling, people understand the same by the same wording. Like, for example, like when we use an example from frequentist analysis, let's say positive emotions and depression, some people would correlate it, some do mean difference checks, some people do a regression from A to B. So it's like similar but different somehow. And I wondered if if the Bayesian approach is a bit more, let's say, standardized, how you see it.
So if the I'm still not sure if I get a question correctly, but if you're interested in the general difference between the Bayesian approach and the frequentist approach, is that in the Bayesian method, we have the uncertainty part that we mentioned many times. So in the coin flipping or water land example, we have the entire posterior distribution, and we do not have a single point estimation. We get the uncertainty, and then the uncertainty is quite important. And if, for example, we have more than enough data, we have data of weight and height information from 10,000 people, and we can do a simple linear regression. We could do the simple linear regression we could do the simple linear regression analysis in two ways. One way is to use frequentist linear regression, and another way is to use like a Bayesian Stan version of linear regression. And what you can compare is the posterior distribution of the slope and versus the single point estimation of the slope using frequentist analysis. And if we have more than enough data, I don't really think there will be too much difference. So I'm not sure what you mean by more coherent results.
Yeah, I think I will just I will just write you an email or something so we don't have to like block the whole seminar.
Okay. Yeah.
Sorry.
Yeah, no worries. Other questions, comments? Okay, good. So now we can go back to the task. So let me just show you again. So here we have two choice options, and we make a choice, and we get a reward, and we make another choice, and we get punishment. So this is the task, okay? We are fine with that. And let's just ask ourselves, or maybe before that, we can just name them. So here, this is the choice presentation or representation. So this is the breakdown of different stages of the decision making. So, and then here, this one is second, the action selection, and here it is the outcome, okay? So here I show you what you can see from the data. So what you cannot see is, in between here, there's the valuation part, or making the prediction. And here, from the outcome to the next action, so how you use the outcome to educate yourself, to improve your behavior. This is also not seen. So those are the internal parts, or most of the time in the literature, they are called the latent decision variables, because it's hidden, so then it's called latent, and they are related to decision making, so then they are called decision variables, okay? So latent decision variables. Those are something you cannot see from only purely the behavior. And this is one other justification or motivation to use cognitive models, because only with cognitive models or computational models, you're able to see the internal steps or internal variables that is otherwise not possible to uncover by purely looking at the behavior. Good. With the data, we can basically ask ourselves. So if we are now go back to the role, okay? Now we are experimenters, not participants anymore. So we are experimenters. We send out the experiment to different people, and we collect the data. And suppose you are the experimenter, and you basically ask yourself what you know about the data, okay? So what do you know about the data? And the idea is that you could imagine there's a data table, and you could imagine that we have Excel, and we have some kind of tabular shape. And you imagine what do you know already? So what do we know? What's here? What do we know about the data? Okay, think about just maybe 10 seconds. So think about the task. So there are two options. There's a choice, and then there's the feedback. I already told you, okay? So what do we know? So we know the choice behavior from the participants. So we know A or B, and we know win or loss from the participants. Okay, so those are the data. So those are what we know already. We know the choices, we know the outcome, okay? Those are what we know. So what we can measure by using data before we really go into the modeling part, we can calculate the choice accuracy per person. So I told you already, maybe out of 100 trials, how often the person is making the correct response. So you divide it, and then you get a single number. So the proportion or the ratio or the accuracy, however you call it. So that's something we could simply calculate without really going into the modeling part, okay? And if we do not really use a model, this is usually already the end of the data analysis. We calculate the averaged choice accuracy per person, and then we can maybe say, okay, we do a median split, and participants who are above the median, they perform relatively well, and the participants, they are below the median, they perform relatively suboptimal. Okay, and then we make some further analysis. For example, if we also measure some IQ or whatever, and then we do some correlation. Good. And what we want to do now is that because we have the framework and we have the task, what we want to do now is here. So we would like to know the learning algorithm by using the reinforcement learning updates or the framework. So this task, because I'm showing you this way, so this task is really the simplest task, the exemplar of the reinforcement learning task. So we could use that for the modeling. Okay, good. And this is the part that we have not known yet. Yeah, accuracy. Okay, good. I told you. Perfect. So now is there's another term. Okay, reinforcement learning, and this one is the Rescorla-Wagner. So what is that? So if you kind of look at the textbook, and sometimes people will see, they would consider the Rescorla-Wagner model as the simplest reinforcement learning model. And this one is not really from 1990s, this is from even earlier, 1970s. So they are not computer scientists, by the way. So they are the psychologists, honestly. So they are psychologists. So they would like to use some mathematical formulation to approximate learning behavior in animals initially. So they are trying to understand Pavlovian conditioning, okay? So this is the initial task. And later, so we could use the same thing to understand human behavior because that's somehow the same thing most of the time. Good. And say, before we go into the detail, we could try to differentiate two parts in the cognitive model. So this is universally true. I think, yeah, this is universally true. Whenever we are talking about a cognitive model, there are always two parts. So one is the implementation part, or maybe we can say the cognitive part. Cognitive parts means how participants is computing using some internal steps or internal decision variables, and how those are calculated. So how those internal decision variables are calculated. And then this involves cognitive process. So then this is why it is called cognitive model or the cognitive part. And when we have the internal decision variable, how we could use the internal decision variable to make the choice. So go back to the previous framework. We make a valuation or prediction. So which one has a higher value, which one has a lower value. So then we use the value information to make the choice, okay?
Ich habe jetzt ein Skype-Meeting eigentlich, aber
So here, in this sense, is that, well, we would like to connect the internal decision variable with the actual data. So this is called the observation model, okay? Okay, I repeat here again because this is noisy in the background. So any model, we have the cognitive part. So we calculate or compute what the cognitive process is, what the decision variables are. And those, for example, are the value, the utility, the prediction error, something we calculate, depends on how we formulate the model, okay? Good. And when we have the internal data, when we have the internal decision variable, when we have the prediction error, for example, how this internal decision variable can be connected with the left or right decision. So those are the actual data, right? We need some function to connect the internal part with the observed part. Otherwise, how we make the connection? Okay, good. So if you follow what I'm saying, this is the same as constructing a likelihood function in our previous term or terminology. So, or in the STAN in the STAN workflow. So go back a little bit to think about what a STAN model consists of. There's a STAN model, the first block data, second block parameter, third block model, okay? Data is what we know. In this case, we know the choice, we know the outcome. The second block is the parameter. I haven't told you what parameters are in this model, but let's say there are some parameters, 2, okay? And the model block, that's important. So that's the likelihood function. So that is the place we define the connection between the model and the data. How we could draw the connection to make it together, okay? So we would like to use some statistical distributions to describe how the actual data is distributed following some cognitive process we define, okay? So here is the cognitive process we define, and here it is the statistical distribution part, okay, good. And then this distinction is true for nearly all the cognitive models you will see in your career, I guess, if you stay in science. Nice. So what we will do now is we will focus on first here, the cognitive process, to see as one example how the internal variables are calculated. And then we use the internal variable to make decisions. We're using some observational model, okay, here, the second part. So I will just give you different explanations given the step. Perfect. So now I give you some more introduction of the Rescorla-Wagner model. So I told you they are psychologists, honestly. And the Rescorla-Wagner model, the simple idea is that people, human or animal or just other individuals, they use error to educate themselves and then to learn. So in other words, this is error-driven learning. Okay, you use the error to drive some new learning. Good. And another property of the Rescorla-Wagner model is that the change in value is proportional to the difference between actual and predicted outcome. So this one is maybe not really straightforward to understand, but I will show you what that means, okay? And this one I'll tell you later what that means. So this is the task, the option, and you make an action and you receive the feedback, good. Now this is the core part, okay? After nearly 1 hour, we finally go to the core parts of the model. So there are 2 steps. One is to calculate the prediction error. The other one is to draw the value update, okay? Let's start with here, the prediction error calculation. So if we look at the literature, prediction error is in fact one of the most mentioned term and also one of the most studied kind of phenomenon in the world of decision-making and reward learning, reward processing. It is first studied not really in human, in mice, as I recall, and from also more than 20 years ago. So there's a study to study the dopamine neuron firing that is related to the reward prediction errors, the anticipation, okay? But anyway, there is something called reward prediction error. And what reward prediction error means, it is that, actually written here, the difference between actual and predicted outcome. So that's the difference between what you get and what you expect. So this is a simple idea. So in equation, it looks like this. So the capital R means the actual reward. So it can be either a reward or a punishment. So let's call it outcome because outcome contains both the valence. It can be positive, can be negative. So okay, so actual outcome. So this can be a win, it can be a loss. The V, so what is the V here? The V is the idea I try to convey for multiple times. The value, the subjective value, so the valuation or the prediction, they mean the same thing here. So what do you think that you will get? So then translating that to some like human knowledge, this is what you actually get, and then this is what you think you will get. And here, there's also another illustration. Reward, actual reward, obviously. Here it is expectation, current expectation. And then if you calculate the difference, bam, that's the reward prediction error, right? So this is as simple as that. But don't feel really scary to look at equations. That's just terms to simplify ideas. Here they are, this in the blue frame, it is the same as in the red frame. So one is formulated in mathematical notions, the other one is formulated by language, okay? But you will see they are the same, and this is more concise, honestly. Okay, go back. So reward prediction error, let me just repeat. I do not feel that it's annoying to repeat because this is important. I repeat multiple times, and you could also learn or memorize by multiple times of input from me, okay? Prediction error, the difference between what you actually get and what you expect that you will get. So the actual outcome and the expected outcome. You take the difference, that's the prediction error. Very good. The prediction error here, this is the same. The prediction error here is then used to update your next value or your next expectation. So the general idea here is we use the feedback to educate yourself to update our value. So here the feedback is taking place here, and the feedback is not really actually the feedback that is teaching us to update. It is the prediction error term that teaches us to update the value information. Okay, good. So when we have this term, the difference, this one, the next step, we will use the prediction error to update our value information or the valuation. And how this update works, okay? This is the second explanation. So we look at here, the V, we know and understanding the V basically means the value, the expectation. And then we have to look at here the T. The index T is trial. So T means the current trial, for example. And T minus 1 simply means the previous trial. Update. So just tell me what update means. Update means we have something old and we have something new, and we update from something new. We update from something old to something new by some calculation, right? So this is the meaning of update. Something old is here. This is old value because that comes from the previous trial. And V of T is something new. So this is the new value. We update from the old one to the new one, okay? If we only look at here, that means the new one is the same as the previous one. The update basically means there is an identical update. There is really no update, basically. So what is actually the actual updating part? It is this. So it is the prediction error multiplied with a free parameter alpha. So the free parameter don't really get scary. Free parameter is the same. It is just the same as the slope in the regression, the intercept in the regression. This is a free parameter we do not know, but we could infer from the data, right? So for a simple regression, before you have the data, you never know what a slope looks like. It can be positive, can be negative, can be flat, right? We have no idea, but it is a free parameter. So we have already been dealing with free parameter for multiple years, I guess, from your educational experience background. Good. So this is just a free parameter that calculates or quantifies how much the reward prediction error will be used to update the value information, okay? So Let me give you some example. Otherwise, it's a little bit too difficult to understand. So let's say the reward prediction error is 0.5. For some reason, it's 0.5. Okay, just 0.5. The alpha is a parameter by definition takes value only between 0 and 1. So that means how much proportion of the reward prediction error will be used to update the value. So if alpha is 0, that means none of the prediction error will be used to update the value. So if alpha is 0, old value equals new value, no updates, period. If alpha equals 1, so that means 100% of the prediction error will be used for the updating. Okay, so here then it will mean that new value equals old value plus PE. Okay, good. And if this alpha is 0.5, so that means simply half of the prediction error will be used for the updating. So translating that, that means new value equals old value plus half of the PE. Okay, as simple as that. So you can now imagine when alpha equals 0.2, then that means 20% of the PE is used for updating. If alpha is 0.8, that simply means 80% of the prediction error will be used for the value updating. It simply quantifies how large of the proportion, how large proportion of the PE, the prediction error, will be used for the value updating. Okay, good. So now I can tell you what this means. In the red frame, it says, it's basically translating what we have seen from the formula or the equation to some human language, for example. So the expectation on the next trail, so VT equals the expectation on the current trail here, this VT minus 1, plus the learning rate multiply with the prediction error. And the prediction error literally means the difference between the actual reward and the current expected reward. So this is the entire part of the simple Rescorla-Wagner value updates. Okay, so there are two important internal variables. So one is the V, the value. The other one is the PE. Okay, the R is the actual data, the actual what we have seen win loss, and V and PE, they are internal variables. Alpha is the free parameter. Okay, good. Understanding the learning rate, we don't have the time for that. We will talk about that the next week, but I can answer the question. So can one argue that a higher learning rate always leads to quicker optimization of the model? That's a very good question, and we will talk about that the next week. Simple answer is it depends. Sometimes maybe higher, sometimes maybe lower, but I will explain later why that depends and depends on what. Yeah. Any other questions, comments? So today I will send you the slides, even including later materials, and you can take a look. But next time we will also cover everything together, okay? You can also tell me now if I spent too long on this, because it's obvious and maybe I've spent 5 minutes is enough rather than 15 or whatever. Because I thought to most of you, this might be relatively new, and I guess I would take the time to go a little bit slower to explain everything step by step. Okay, could have been a bit faster. Okay. Yeah. Any other questions? Did I answer that? The learning rates, the higher thing? It depends, right? Yeah, I see. So yeah, good. Yeah, I have the same feeling. So sometimes I think I repeat a lot the simple stuff. In the task of slot machine, would expect higher learning rate would lead to quicker adaptation. No, it depends. No. It really depends. It also depends on what you mean by adaptation, but no, not always. So most of the time it depends on the reward probability. And that's something I will tell you later. Yes, this is correct. So higher learner rate means you also get more easily distracted by improbable results. Yes, this is correct. So this goes two ways. So if you have a high learner rate, you might learn the rewards fast or maybe too fast. But that also means if you receive a negative feedback, you will also get the impact from the negative feedback too large. Which is not ideal, because if you have a slot machine that has 80% reward probability, you know by chance 20% of the time it will give you a negative feedback. But as a rational player, you might ignore it because you know on average this is still a good machine and you do not really care if once or twice you get a negative feedback. But if you have a higher reward learning rates, this negative feedback will really drive you crazy because you will take that really, really seriously. So why are you not using V of t mean of all the previous trials? This is not necessary. It is because there is the update, right? The update is coming from the first trial until the current one. So the previous here, I can show you. So V of t mathematically already contains all the information from the past. So that basically means all the past information is compressed in the V of previous trial. Yeah, good. Another question, so does this mean that it just sets the weighting to value new data more highly than data already in the model? So there is no setting thing. What do you mean by setting? Do you mean to set a learning rate? Yeah, okay. I sometimes see there's a confusion. So if I teach whatever, so I see feedback that people say whenever I tell them this, and then they say, does this mean that I have to set a parameter for this person and set a parameter for that person, and then to depend on the data? No, the simple answer is no. It is because the parameter is something we estimate from the data. It is not something we set beforehand. There's nothing we predetermine. We predetermine this equation. This is we predetermine. Otherwise, we cannot go forward. But we cannot predetermine the value of the parameter. So I always make the analogy. This parameter is the same as the slope parameter in the linear regression. You never really set a slope for the data, right? You estimate the model and then you obtain the parameter, the slope for the linear regression. So here the same idea. You use the data to estimate the parameter rather than you set it beforehand. Yeah. Okay, so you mean that with the higher learning rate, it values new data more highly? Yes, this is correct. Yes. Good. This is very good. Any other questions? I guess maybe just 5 more minutes. If you are busy, you feel free to leave and you can watch it later. But for the others, if you would like to stay, I guess I can just quickly talk about this because you're asking, and most of the questions, you are really hitting the right point. Very good. So let's understand the learner rates. with first one example. Suppose the learning rate is 0.9. This is a high learning rate. So suppose the initial value is 0, and then suppose that we observe a positive feedback. And then we can already calculate the next value according to the equation, okay? So learning rate multiplied with 1 minus 0, and then we get a 0. So the value is 0 in the first place, and it is updated to 0.9 in the second place, okay? This is the value update, how the value update works. And then what we could do is that we plot it. So suppose that we have 20 trials of data, and the gray here, the gray line is the actual feedback. If it is 1 here, that means reward, 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 and there is 1 punishment, another punishment, and multiple times of reward, 1 punishment, reward, punishment, good. And when we have the reward information, we can basically calculate the trial by trial value. So here is 0, the same as here. The second one is 0.9, and then it goes up, good. So as you could see easily, if the environment is always rewarding, coming from 0 to 0.9 is really good, very nice. But whenever we have a negative feedback, the value drops hugely, because whatever it learns, it only gets the impact from the most recent feedback, the negative one. And then there's a huge decrease. And we know that this is a good option. We know that this has a 80% reward probability. So maybe we do not want to overreact on the negative feedback. We do not want to be oversensitive to the negative feedback. So then we could do it a little bit differently. So what I plot here is the value curve according to different learning rates, 0.9, 0.7, 0.5, and 0.3. So you see here in particular the 0.3 example, the increase of the value. It is a little bit slower, okay, good, but it still increases. That's the trend, that's always the case. And so here, that's the symmetrical part. If we get a negative feedback, here, negative feedback, then the decrease is not so huge. So it will not be hugely impacted by the most recent negative feedback. So this is the idea. Good. So then, so why it is the case? So conceptually, I guess a lot of you already understand that higher learning rates means you weigh the most recent outcome heavily. Conceptually, yes. And mathematically, you can also prove that. So here it is the standard way of writing the Rescorla-Wagner. You can rewrite it. So rewrite the V of t in terms of the reward and the V0. Okay? Don't worry if that looks a little bit too complex. That doesn't matter. What we want to look at is only here, this part that I show you, highlighted. And this part can be plotted. So this part, if you plot it, you will see this graph. So on the x-axis, that's the trial number. This is the current trial. This is the previous trial. Previous 2, 3 back, 4 back, 5 back, 6, and 7. So trials in the past history. The color coding is the same. The darker purple is 0.9, here 0.7, 5.3. Those are different learning rates. And this plotting basically means how much you weigh this outcome according to the relative position. So here, when you have a high learning rate, the most recent outcome will be weighted heavily. But even 1 back, it will be weighted a lot lower. And then this one is already close to 0. And when you have a lower learning rate, even though the most current one is not really weighted too much, but all those information in the past, they have some contribution. So in other words, that means if you have a lower learning rate, it creates a buffer zone. So if you have win, 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 loss, but most recent one is the loss. So all those previous positive feedback will create a buffer zone so that the most current negative feedback will not really impact so much. Okay, so this is the conceptual idea. If you want the proof, look at here. If you want the conceptual idea, look at here. Enough. Yeah, good. the comment is, so when you arrive at prediction of value 1 with high learning rates, there's a number of outcomes that support this before a negative one appears. Before a negative one appears, have no influence on the effects of this negative outcome. It will. So in this case, the darker purple. So this darker purple, it is near close to 1. It is close to 1, it stays there. And if you receive a negative feedback, and then it changes, right? No, does that answer the question? Yeah. So if you mean those values who are supporting this positive value in the past, then no. If you have a higher learning rate, all those past positive information will not really be contributing to here. It will be it will be mostly influenced by the most current negative feedback. Yeah, this is also correct. So there is a comment to say, can the value go above 1? No, the value is in between the range of 1 and -1. This depends on how we define the value. So if we define the value to be 2, if we get a positive reward, we code it as 2, and a minus reward loss, we code it as -2, then the value will be between -2 and 2. There's another comment to say, so it is a way to modify sensitivity to change in data across time. Yeah, in a way, yes. Yeah. So if you have a higher learning rate, you're more sensitive to the most recent outcome. If you have a relatively lower learning rate, all those past information, they contribute to the current value information. That's here, yeah. Are there any other questions? I guess I should stop. But just let me know if you have other questions. The question is, would we need more data to get the same results with a lower learning rate? No, I don't think so. No. So here is maybe just 2 more minutes. I should really stop. So you basically can ask me, what is optimal learning rate, right? So I told you the meaning of a high learning rate and low learning rates. And it depends on the environment. Sometimes the high learning rate is good, sometimes the low learning rate good. I told you it depends, but depends on what? First of all, depends on the reward probability of the task. So if you have a reward probability 80-20, that means it's rather stable. It's not changed too often. And if you have a reward probability of 55-45, oh man, that's really nearly like random. So the environment changes a lot, okay? And if you have also a reversal learning task, so one option is 0.8 in the beginning and becomes 0.2 and in the second part of the experiment, and changes back and forth a few times. So this means the task is certain, the task is uncertain. The task is really uncertain to the participants. So the general conclusion is that if the task environment is stable, a relatively low learning rate is more preferred. If the task environment is volatile or less stable, the relatively higher learning rate is much more preferred, okay? And how to get this kind of optimal learning rate? You can run simulation. And if we have a 28 example, as I showed you before, we run the simulation, then the optimal learning rate is not too high. It's relatively low, honestly. It's 0.18, so it's close to 0.2. And it does not really need more data to make this simulation. If I run the experiment for 50 trials, or 40 trials, or 60, 70 trials, I always get this optimal learning rate. So you do not really need more or a lot more data to get the optimal learning rates. Good. I won't go further, but I can still answer questions. 1 or 2 minutes. Yeah, okay. If no more questions, then see you next week. I will send you some papers to read because it's a little bit difficult to explain everything here. All right, then bye-bye, see you next week.